Hi students, so let us continue the discussion in the synopsis of this waves chapter. So in the last video, if you remember, we discussed uh, standing waves in open pipe and closed pipe. So in closed pipe, I told you that if you remember that this is closed end, so this will be node, this is open end, so this will be empty node. The first mode of vibration will look something like this, right? Now here, this length is L. So we wrote this fundamental. We wrote the length of this equals to this wave is 1/4 of the complete wavelength, right? Complete wavelength will be this much, right? This is one wave, one lambda. So this is half lambda. This is 1/4. So 1/4 of lambda. So lambda was equals to 4L. And from here frequency we write V by 4L. And the next one will be, since this is closed pipe, the next mode will be, next harmonic will be third harmonic, right? Because only odd harmonics are allowed in closed pipe. But there is a small detail here which we have not discussed in the last video, and that is, most of the time this is the formula that we can use, we can be happy with. However, this is not perfect. The reason is, since this end is open, the air here, the air molecules or the air, while vibrating, will go much beyond the length of this pipe. So the shape of the waveform will slightly go outside this. Okay, slightly go outside. So let me try to draw with this with a different color. So slight, little bit outside, you expect the oscillations to continue. Okay, so this much of, if this is the length of the pipe which we assumed, this much will be the end correction, E we write. So E represents the end correction. Okay, so this tells you how much further the air can go while oscillating here back and forth, and that has to be considered while writing this formula if you want the exact one. So if end correction is asked to be neglected in the question, then you can live with this formula. Okay, you can continue with this formula. But if end correction is mentioned, then this length L cannot be told as this 1/4 of wavelength, right? So now L plus this E corresponds to 1/4 of wavelength. Okay, in case of uh, closed pipe. So fundamental frequency will be what? V by 4L, and L will be now, see, length will be 4L plus E, so it will be L plus E. So L has to be replaced by L plus E. Now what is E? Well, detailed experiments have been done to show that E is equal to 0.3 times diameter of the pipe. So usually this pipe will be cylindrical, so the D is the diameter. And if you write in terms of radius, it will be 0.6 times radius. Okay, so R is the radius. So this happens in case of closed pipe. In case of open pipe, okay, since both are open, your air, the waveform will look slightly like this. So little bit outside it will go. Okay. Here E, here E. So now this is the length of the pipe. So L plus 2E, this E plus this E will correspond to 1/4 of wavelength. So lambda will be 4L plus 2E. Okay, so frequency will be velocity by wavelengths of L plus 2E, and E is given by the same formula. So this has to be remembered while using, while keeping in mind the end correction. Now, if diameter of the pipe is asked in the question, and if they given you the frequency which is exciting this pipe, then it is very clear that end correction has to be considered if diameter of the pipe is mentioned. Okay. Now, one of the problem which is there in NCRT is a very good problem because it explains the importance of this end correction. Okay, so it is question number in NCERT textbook. You will find this in question number 15.15. Okay, so it is the 15th question in the 15th chapter, okay, which is the last chapter of first P. So if you don't include end correction, you will get very stupid answer. Okay, and it is very interesting the way the question has been framed. Okay, so let me let you know. I feel there is a mistake in the question, in the framing of the question. So let me just discuss it. Okay, a meter long tube open at one end. So a meter long tube. So length of the pipe is 1 meter. Open at one end. So it is clearly a what kind of pipe in physics we call this closed pipe. Which is question number 15, 15th chapter. Okay, weight chapter. NCERT. Okay, NCERT. NCERT is not visible, right? So let me write here NCERT. Okay. Now, what they're saying is a meter long tube open at one end with a movable piston at the other end. So the other end actually is closed, but it has a piston which can be moved like this. Okay. A tuning fork shows resonance with a fixed frequency source. So frequency of the tuning fork here is given 340 Hz. So I hope you may be remembering the experiment which you usually do in first PU lab is you have this container containing water and then you put this tube. So this end becomes the closed end and this is the length of the air column which will oscillate. Okay, so this becomes the length of the pipe and you can easily change the length of the pipe by moving this tube up and down. Okay, so here they are doing it with the help of this piston. Okay, and then you can bring a tuning fork. Here they have put here in this way. Usually in experiment we bring it this way and the vibration of the tuning fork will try to excite this air and you know that whether this air will oscillate uh, in one of its natural frequency depends on whether the tuning fork frequency resonates with the air column. Okay, so air column has many natural frequencies, right? Since this is closed pipe, there will be odd harmonics. So this frequency of the tuning fork should match with one of the um, natural frequency. Then only the air will oscillate with a nice amplitude and then you will hear a nice sound, right? So that the resonance chapter in the resonance topic in the previous chapter, if you remember, what does it say? It says that if the frequency of the exciting source matches with one of the frequency or matches with the natural frequency of the system, then the system oscillates with maximum amplitude. So here, who is oscillating? The air. So when air oscillates, what do you hear? Sound. Okay. So in this case, let us continue the question. So it says shows resonance. So this tube, the air in the tube shows resonance with a fixed frequency 340 Hz when the tube length is 25.5 centimeter or 79.3 centimeter. So they have not mentioned which harmonic these two corresponds to. Okay, so usually if they don't do, then better to consider this as the first harmonic, which is the fundamental, and this one as the next one, which is the third harmonic. Remember, there is no second harmonic in closed loop. Estimate the speed of the sound in air. The speed of the sound they are asking. Edge effects may be neglected. Edge effects may be neglected. Edge effects may be neglected. Now, does it mean that they are asking us to consider end correction can be neglected because end correction occurs in the edge? If that is the case, then the problem is completely false because, see, let me explain. So if this length corresponds to the fundamental frequency, and what is the formula for fundamental frequency in closed pipe? V by 1 is 4L, 1 is 2L. This closed pipe, more spelling. So we have to write 4L, right? So this is for the first length, L1. Okay. Now, if resonance occurs with this tuning fork, then it means frequency of the tuning fork should match with the natural frequency. of the pipe. So this is the first frequency of the pipe, so this should match. The second one I assume is the third harmonic, so it will be 3 times V by 4 L. Now L cannot be same, right? How can you write same L? Because the exciting frequency, which is the tuning fork, is fixed, so frequency is fixed, so this has to be different, L2. So let me remove F1, okay? So let me write it here nearby. This is frequency of tuning fork. So one frequency you get this second, both are same frequency, but this is corresponding to first harmonic, this is corresponding to third harmonic. And how you did that? By changing the length. Now observe carefully. Frequency of tuning fork is mentioned, right? Length of the pipe in the first harmonic is mentioned. Length of the pipe in the third harmonic is mentioned. So if I use this formula, cross multiply, I can find the speed of the sound here itself. The cross multiply. See, L1 you know, frequency of tuning fork value, or you can use this formula, right? But if you can use this itself, then why this information was given? And if you use this formula or this formula, you should get same answer. V is same. Speed of the sound is not dependent on this length, right? I'll talk about speed of the sound formula a little bit later. So it is very clear that you have to consider the end correction, because if you use this formula without end, these formulas are without end correction, remember. So if you use this formula without end correction, you are not going to get the right answer. In fact, you are not going to get a you're going to get a stupid answer. This formula will give you one speed of sound, this formula will give you one speed of sound. And some students will argue why this formula is needed, I can use this itself directly, right? So in fact, you can observe that it is wrong also, because see, according to these two equations, if you observe carefully, this is same. So that means 3 by L2 should be same as 1 by L1, right? V by 4, V by 4. Frequency of tuning fork, frequency of tuning fork. So 3 by L2 must be 1 by L1 cross multiply. L2 should be thrice of L1. So is this thrice of this? No. 3 5 is 15. This is 3. So clearly there is something wrong going on. Okay. So we have to consider the end correction. But when you read the question, you feel like they are saying you can neglect the end correction. If you neglect the end correction, then your result will be absurd. Okay. So let us include the end correction. Now, if you include the end correction, then in the first harmonic, what was the shape? Like this, right? So it was L1 plus E equals to lambda, first wavelength. Yes or no? Here lambda will be same because we are keeping the frequency of the tuning fork fixed. And second will be L2 plus E equals to lambda, right? So let me draw this shape. Okay, not lambda, sorry, lambda by 4. And this will be 3 lambda by 4. Remember this, okay? So it was like this, right? So a little bit out it will come out if there is end correction. So L plus E equals to lambda by 4. This is second resonance for different length. So it will be like this. It will be like this, okay? Like this, okay? So this is your third harmonic. So L1 plus E equals to lambda by 4, L2 plus E equal to 3 lambda by 4. So you can now see that L1, L2 need not be same because this E is there. I mean L2 need not same, L2 need not be, see if this E was not there, L2 will be what? 3 times L1. But now L2 need not be 3 times L1 because this E is there. So since E is not mentioned in the question, diameter of the pipe is not mentioned. So what we will do? Subtract these two. So L2 minus L1 will be equal to 3 lambda by 4 minus 1 lambda by 4 will be 2 lambda by 4, which will be lambda by 2. So lambda will be what? 2 times L2 minus L1. So once you know this, then you can find the velocity by writing frequency into wavelength. And that will give you frequency of the tuning fork, you know already, 340 into wavelength is 2 L2 minus L1. Now L2 and L1 are mentioned to you, so you can easily calculate. So I hope you understood what is the use of end correction in such problems. So we have completed standing waves, including the end correction. Now we will quickly discuss beats. So in beats, what happens is waves, two traveling waves with slightly different frequency, traveling in the same direction, overlaps. Okay, so one is like this, and the other one is, let's say, like this. Okay, so this frequency is F1, this frequency is F2. So when these two sound will overlap, okay, at a given point, okay, this is time. Okay, so with time, this is how the displacement produced by the two waves y1, y2 changes. So if this has frequency F1, this has frequency F2. When they overlap, you will find that the resultant sound, you can see it, that right now you can see positive maximum of this and positive maximum of this overlap. Somewhere here you can see positive and negative are overlapping. Again, if you see positive, positive, almost like positive, negative. So what is happening is, at some instance, see time, okay? At some instance, the positive of this and the positive of this meet, meaning their two waves are in the same phase. So that time you will get a large amplitude. And then when the positive and negative meet, you will get less amplitude. And again large amplitude, then again less amplitude, large amplitude, and again less amplitude. So I'm not drawing the diagram exactly, but the point is the amplitude now increases and decreases with respect to time. So if a sound, if this is ting like that, and this is tung like that, because this is higher frequency, the pitch will be more. When they overlap, your sound will be like that. So the sound will increase in intensity, then decrease, then increase, then decrease. So this increase and decrease in the intensity of the resultant sound, when two traveling sound waves traveling in the same direction, but with slightly different frequency overlap, then you get then you get beats. This phenomenon is called beats. Okay, so the frequency of this is still high only, right? It's still comparable to this or this. So the frequency of the resultant sound is given by the average of the two frequencies. So this is the frequency of the resultant sound. But you can see the amplitude itself is oscillating, is changing. So the frequency with which the intensity of the sound oscillates, meaning how many intense sounds will you hear per second. Okay, that is called beat frequency, and that is given by f1 minus f2, or it can be f2 minus f1 depending on whichever is greater. If f1 is greater, you write this formula. If f2 is greater, then you write this formula. Why? Because frequency cannot be negative. Why? Frequency is number of something, right? Number of oscillations. Number of something cannot be negative. Right? How many apples are there? 2 are there, 0 is there, minus 10 apples we cannot say, right? So number of something cannot be negative. Okay, so this is the formula for beat frequency, which means number of intense sounds heard per second. Intense sound heard per second. And this is the frequency of the sound. The sound itself, I see this y itself has a frequency, but here the amplitude itself is changing, therefore amplitude also has a frequency. The variation of the amplitude also has a frequency. So keep this in mind, and let me quickly tell you what kind of problems are expected from this. Also, the frequency of the two waves should not be very different. Okay, it should not be very different. If it is very different, if it is, let's say, if this is 1000 and this is, let's say, 1000, this is 900, and you get 100. Now, if it is 100 hertz, if the sound intensity varies 100 times per second, then the variation is so fast that your brain cannot sense it. You see, when you hear one sound, it lasts in your brain for a certain period of time. We call that persistence of sound, right? So if you want the sound intensity variation, no, if you want to hear it clearly, then you need some proper gap between them. The proper gap will happen when the frequency is little bit less, right? It should not be too large. If frequency is too large, then it means it is making many, the amplitude is changing so fast that you hear one big sound, then before you hear the, before the low sound comes, you immediately hear the big sound. So the big sounds come so fast that you don't hear the low sound, or you don't sense the absence of sound in between two big sounds. Okay, so keep in mind that the frequency should not be too large. The beat frequency should not be too large, meaning these two should be close to each other. Okay, so once we know this formula, usually you will get this kind of questions in NEET or CET. So you will have two tuning forks. Okay, so this has frequency, let's say 300 hertz. This has unknown frequency. Okay, try to understand this. Now, when you beat them, okay, in some double pads, they produce sound, which has sound has frequency 300 hertz. This has unknown frequency. Now they are slightly different, let's say. So you will hear some beats, and those beats frequency is equal to, let's say, 4 hertz. Then they will ask you to calculate this. Now you will say, Ares, it's very easy because you know the formula f beat equals to f1 minus f2. So if you substitute f1 300, beat frequency 4, you can easily calculate f2. What is the big deal? Problem is, this is true or this can be also true, right? I have told you before. f2 minus f1 can also be true. If you use this formula, you get different answer. Try to substitute and check. So point is whether to use this formula or this formula, equation 1 or equation 2. So right now we cannot decide because f2 we don't know, right? So how can I decide f1 is greater than f2 or f2 is greater than f1? So in this case, they will include one more information. So they will say one of these tuning fork will be either loaded or they will say it has been filed. Okay, so these two words they use. Okay, one of the tuning fork, either this or this, I don't know, number one, number two. Okay, so when you load, usually you load wax. Okay, so what happens? The frequency will decrease. One way of remembering is when you load, it becomes a little bit, inertia will be more, mass will be more, so frequency will be less. It will not be, it cannot change faster, right? And when you do filing, filing means you are in a way making thinner, then the frequency will increase for whichever tuning fork you are loading or you are filing. So they will tell you one information. So let us assume they are saying in this particular question that tuning fork 1 is loaded, okay, and beat frequency has become 6 hertz. Suppose this data, then we can decide which formula to use, because if this is loaded, okay, if this is loaded, then frequency of this will decrease. So f1 will decrease. So f1 will decrease. F1 will decrease. F1 will decrease. Now, they have told beat frequency becomes 6. What was the beat frequency before 4? Now it has become 6. So beat frequency should increase in the question, according to the question. Which makes sense and which makes no sense. If this decreases, how can this increase? Right? Sometimes students don't understand this. Is 10 minus 2, 9 minus 2. If this number decreases, then the answer will also decrease. No, this is 8, this is 7. But this is, here it has increased, but it should decrease. So come to this formula now. If this frequency decreases, then this increases. See? And according to question, they told beat frequency increases. This is the right one. So once you know which is the right one, beat frequency will be 4. F2 is F2 only, and we have to find F2. F1 is 300. So from here F2 can be found. So this is the this is how we are solving the problem by this information. Okay, so you have to remember, when you load a tuning fork, frequency decreases. When you file a tuning fork, frequency increases. Let us say another example. Suppose frequency tuning fork 2 is filed, and let's say beat frequency became 2x. Then which formula will you use? The first one or the second one? Okay. So forget this errors right now. Okay, let's understand. Now, if 2 is filed, tuning fork number 2 is filed, then frequency of number 2 will increase. So F2 will increase. So F2 will increase. According to problem, bit frequency which was 4 has become 2. So bit frequency has decreased. Now, if this increases, this will also increase. But here, according to question, it is decreased. So this cannot be right. Here, if this increases, this will decrease. This is correct. So this formula you should use. So that way you should be able to decide which formula to use. Sometimes one of them may be tuning fork and the other one may be string. So in case of string, loading and filing cannot be done. So in case of string, what they can do is they can increase the tension. So if you increase tension, then frequency will increase. Why? What was the fundamental frequency of a string V by 2L or nth harmonic means n times V by 2L. And what is V? Root over tension by mu. So again, instead of, if they don't mention tuning forks, they will mention string. And in case of string, how would you change frequency? By changing the tension. Okay. One very interesting problem is there based on this. Okay. So let's say you have a string and you have a tuning fork. This is system 1, system 2. This produces frequency 200 Hertz. This is unknown. Okay. And right now beat frequency is 6 Hertz. I want this. Information given is tension in the string is increased, because of which beat frequency has become again 6 Hertz. Now what will it do? Because now I have given 6 on. So let us write the formula once. What are the two possible formula? Beat frequency is F1 minus F2, or beat frequency is F2 minus F1. Okay. So let us say beat frequency is initially how much? 6. So this is 6. Okay, 6. F1 is 200. 200. Here beat frequency is 6. F1 is 200. Right. Now, if you use this formula, what will be your F2? This will come here, this will come here, so it will become 194. And here F2 will be 206. Right? So, which is the right option? Only one can be right, right? In hertz, okay? I am not writing the units. What they have mentioned, when tension is increased in this wire, then what will happen? Frequency of F1 will increase. So, this 200 will increase, this 200. And beat frequency again became 6. Now, where is that possibility? See, F2 is 194, right? If this is correct. So, 200 minus 194 will be 6. Now, tension is increased, which will increase the frequency of the string, meaning F1. This is F1. So, if this increases, okay, if 200 becomes more than 200, 200 minus 194 will not be 6 again, right? How it can be? 200 minus 194 is giving you 6. If this is the right equation, then that will give you answer 194. Now, if this increases, how it can be again 6? Okay? 200 more than 200, if you subtract with 194, you cannot get 6, right? But now you see here. Right now, F2 is 206, right? So this is 206, this is 200. Now, they have increased the frequency of the string. So if this increases, this is 206, remember, 206, let me write. If this increases and if this becomes, if you keep increasing, when it becomes 212, this, then 212, now this is because you write this one first, right? Frequency is always positive and 2. So 212 minus 206 can again give you 6. So this is the right equation which we have to use. This is the answer. Okay, I hope none of you are confused. So this is all about beats. I have discussed the important problems also. Another thing I would like to tell you, which I missed out in the previous video, is when I was talking about speed of sound in air, right? That formula is given by root over bulk modulus by density. In case of string, what it was, we remember root over P by mu. So T is basically the property of the string which brings it back, right? So if you plug it slightly here, and tension here and tension here will create a resultant tension here which will bring the string back. So tension in a way acts like the elastic property, and mu has linear mass density. So the wire is linear, right? So the mass is stretched in a line. So this mass plays this mu plays the role of inertia. So in any way, these two properties are very important. This itself has been asked in one of the CET exams. That what two properties a medium must have so that it can waves can propagate. One is elasticity, other is inertia. So here, in case of sound, when it travels in air, what happens? The air gets compressed and then it gets decompressed, right? So this compression, decompression, which is called compression rarefaction, travels through air. So when compression occurs, a certain volume of air is there, right? So when compression occurs, volume increases. Volume decreases, pressure increases. So change in pressure, change in volume is related here, and that is related to what bulk modulus, right? We all know the formula for bulk modulus, volumetric stress by volumetric strain. dV by V, we will go here. And minus sign is there to represent when pressure increases, volume decreases. So bulk modulus plays the role of your elasticity. And here we are talking about air. So in air, the mass is obviously not in a line, it is in a 3D space. So you will not have linear mass density, you will have the normal density, which is mass by volume. So this is the formula for speed of sound in air. In solids, if they ask, the speed of sound is replaced, the bulk modulus is replaced by Young's modulus. Okay. There is a interesting question which students usually ask is, this is for solid, okay, solid. This is for gas or liquids. Now concentrate here. Density of solid is more than density of gas. So if this is more, this should be less. But actually speed of sound in solid is more. And that is because Young's modulus of solid is much more than bulk modulus of gas. Solids are more elastic compared to your gases. So therefore, though this will be larger than this for solids, this is way larger than this. So if this increases 2 times, let's say, this will increase, let's say, 100 times. So the ratio will still be more than this. That's why speed of sound in solid is more. Now, this formula of speed of sound, if you apply Laplace formula, then bulk modulus comes out gamma p divided by rho. Gamma is the ratio of molar specific heat at constant pressure divided by molar specific heat at constant volume, Cp by Cv. Now this in turn, if you do the kinetic theory of gases chapter, this in turn is 1 plus 2 by F, where F is the degrees of freedom. For monoatomic gases, degrees of freedom is 3 for mono. For diatomic, it is 5. So if you know the kind of gas, for diatomic, it is 5. So if you know the kind of gas, you can easily calculate gamma. P is the pressure, rho is the density. So the speed of sound formula is gamma p by rho. Don't confuse this formula with RMS velocity of molecules in a gas. That is 3p by rho. This 3 is there. Okay? Once you know the speed of sound in gaseous medium, gamma p by rho, also try to represent this in terms of temperature. So P is pressure, density is mass by volume. So volume will go here, right? PV is what? PV is nRT. Repeated mass of gas is PV is N gas. Okay. Now mass of gas I can write number of moles into mass of 1 mole. Mass of 1 mole is called what? Molar mass. So if it is oxygen gas, then it is 32 grams. Okay. So that you have to convert in kg and then substitute if you want the answer in, meter per second. So this n will cancel. So what is the speed of sound? Root over gamma RT by n. So now if you go back to that open pipe and closed pipe formula, so the fundamental frequency in open pipe was what? V by 2L, which I can now write 1 by 2L root of gamma RT by n. This P represents temperature in Kelvin scale. Okay. So it is called absolute temperature. So the last thing now, which is pending, is Doppler effect. Okay. So let us quickly discuss the important points about Doppler effect. So what is Doppler effect is, imagine here is a source of sound and here is a listener or observer. Okay. Usually in textbook they say observer, but my students will say, oh, what if sir the observer is deaf? Okay, so let us call it listener or detector of sound. Okay. So this source emits, let's say, spherical waves like ripples in the water. So this is the first wave, and as the first wave spreads, the first wave goes here, this becomes the second wave. And as the second wave goes here, first wave goes here, right? First wave reaches here, second wave reaches here, this is the third wave. So like this, the waves are emitted. Now, if this is the observer here, so this observer receives a certain, certain number of waves per second. So that is the, so if this frequency is f, if it emits 3 waves per second, right now let us assume, okay, then this also receives 3 waves per second. But if the source starts moving with some velocity vs, then what happens? Try to understand. Now this is the center of the first wave. In this case, this is the center of the second wave also. But if the source is moving, then the first wave which started from here, right? Right? So the center of this first wave will be here itself, right? So by the time the first wave will by the time the first wave will spread here, the center will be here itself, right? But the center of the second wave cannot be here because the source is moving. Is it clear? So center of the second wave will be here. Center of the third wave will be somewhere here. So you can see this observer now, the waves are in a way getting compressed. So since the waves are getting compressed, the wavelength, which is distance between uh, two consecutive points in the wave which are in same phase, or directly you can say this is the distance between two consecutive crests. Okay, so that wavelength has now decreased. And you know this frequency, velocity of the sound as heard by the observer divided by wavelength. So because wavelength has decreased, frequency will increase. What if the observer was here? Then you can see the wavelength has increased. Now the wavelength has increased, here wavelength has decreased. So this observer here will receive less number of waves per second. Okay. So I hope you got the point. Okay. So basically the idea is, initially as this source emits waves after waves, so first wave is emitted, right, is spreading. Now if the source remains here, then the center of the second wave also will be here itself. Then center of the third wave also will be here itself, right? But let us say the source is moving. Now when the source is here, the first wave is emitted, right? So it is spreading in this sphere. But second wave center will be here, right? So it will spread here. Third wave will be here, right? So this is how the sound waves will appear if you try to represent it in a diagram. And therefore we understand that when the source moves towards the observer, the wavelength of the wave decreases, the frequency increases. Right? Now let us say the source is not moving, so that the wavelength doesn't change. But if the observer starts moving along this line, okay, this is important, along the line joining. So if the observer moves towards or away, then the speed of the sound will change, because if sound is coming this way and observer is also coming this way, then the speed of the sound will be more than before, right? If two objects move in opposite direction, then the speed of one with respect to the other is given by speed of one plus speed of other, right? Relative velocity formula you know, right? VAV equals to VA minus VB, and if these two are in opposite direction, then this is positive, this is negative, so the whole thing will become plus. So if this observer moves, then the speed of the sound will be affected. So this will be increase or decrease, which will in turn change the frequency, increase or decrease. So keep in mind, when the source moves, the frequency, the wavelength of the sound gets affected when the source moves. When the observer moves, the speed of the sound gets affected. And these two together changes the frequency. So once you have understood this, the final formula that we write is, So the frequency which is heard by the observer, which is called apparent frequency is given by the formula V plus minus VO, V plus minus Vs times F. So this V represents the speed of sound in air. Okay, so in air here means with respect to air. So if air itself moves with respect to ground, if there is a windy day, okay, so if wind is, suppose sound is going this way, with speed V in air, okay. Now if air itself is going with this speed Vw, then here you have to replace this V by V plus Vw. If sound is coming this way itself. If sound is coming in the opposite direction, V minus Vw. And if this is the way sound is moving, if wind is blowing at some angle, theta, then you have to replace this V by V plus component of this Vw in the direction of V. So Vw cos theta. Okay, so usually these changes they don't do in CET and NEET exams, but if they do, you know how to tackle it, right? So if air is also moving, which means wind is there, then you have to replace this speed of sound by speed of sound plus speed of wind or minus depending on the direction. Okay, that is the speed of sound in air. What about Vs and Vo? Vs is the speed of the source in magnitude, okay, and Vo is the speed of observer. Okay. Also keep in mind that this Vo and Vs that we are writing. Okay, so if this is the observer and this is the source. Vo represents the speed of the observer either towards the source or away from the source, but it is in the line joining the two objects, the observer and the source. And this is V. And Vs can be either here or here. So now the question is whether to take plus or minus. Okay, so that is decided in a very easy way. Okay, I'll give you the trick. The trick is first you try to remember that whenever these two means observer and source move towards each other, frequency should increase, apparent frequency. And when they move away from each other, frequency should decrease. Apparent frequency should decrease. First you try to remember this. Already I have given you an explanation before, right? Once you understand that, now see, if they say observer is moving towards the source, that means this VO should be such that this frequency should increase because I said towards. Then VO is sitting where in the numerator. So if this has to increase, you must take plus sign. Clear? Okay. If they say observer is moving away from the source, this way, then you know frequency away will decrease. So this frequency should decrease. VO is sitting the numerator. When we numerator decrease this, if this is when numerator becomes less, meaning you have to take minus. So that is how you should decide plus and minus for VO. What about VS? Same way. If source is moving towards frequency of the sound heard by the observer should be more. If this is more, denominator should be less. That means you should write minus if source is moving towards. If source is moving away, frequency should decrease. So this should decrease. So denominator should be increase, should be more. So you should write plus. Okay, so that is how you should decide plus and minus. Try to rewind once and try to hear it properly, whatever I have told. Last point I try to make is sometimes this is the observer, this is the source. The observer will be moving at some angle with respect to the source. So this is VO. So let's say VO is 10 meter per second at some angle 30 degree. Then can I put that 10 meter per second here? No, you cannot. Why? Because you only want that velocity which is along the line joining. Right? See, if two things are moving this way or that way, then we say towards or away, right? So this velocity will have two components, one here, one here. This component will be not cos theta and this is V naught sin theta. This is useless because this is neither bringing the object closer or moving the observer farther. Okay, so if observer is moving at an angle theta, we should only include this velocity. So here we should replace this by P naught cos theta. Same thing if source is moving this way, we will take component of Ps, this is theta, and Ps cos theta, and then substitute here. Okay. So if you have understood this, then let me just quickly discuss one simple problem. So here is a observer. Imagine yourself, you tie a string to your mobile, expensive mobile you can take, and then make it ring, okay, alarm clock or something, and then make it go in a circle, okay, like this. So now, if the frequency of the sound coming from the mobile is, let's say, 300 hertz, then will you hear the same frequency or more or less? Try to understand. Here, this is observer, right? This is source. So at any point, the velocity of the source is tangent to this circle, right? And this is the line joining. So this angle is how much? 90 degree. So this Vs has no component towards or away, meaning there will not be any Doppler effect because this will be, this is the, see, observer is at rest, so this VO will go up. Source is moving, no doubt, but it is moving in such a way that its velocity is always 90 degree with the line joining the source and the observer. But we want relative motion along the line joining the source and the observer. You want some relative motion in this direction. Okay, but if you move perpendicular to this line, then it cannot, this velocity of the source has no component either towards or away. So in that way, this Vs will be 0. So this Vs does not represent actually the speed of the source, which we mentioned right in textbooks. It represents the speed of the source along the line joining the observer and the source. Okay. So I hope all of you have understood this problem. So students, this video basically up to here completes the synopsis of waves as per requirement of NEET and CET. Okay. For further details, for further details like speed of sound, which we have discussed already, but let's say you want to know intensity of sound in decibels, you want to know the pressure variation in sound as the compressions and rarefactions occur. For those videos, for those topics, you please search in my YouTube channel. There is a playlist. Under that there is one topic called waves. Okay, so there you will find some 5-6 videos which covers even the JEE topics. Okay, so you can revise that, and who knows, any question can be asked in NEET, right? There is no compulsion that only these topics has to be there. Okay, so I hope you all have understood and gained a lot of knowledge through this video. So henceforth, let me know which chapters you would want me to prepare a synopsis. Now from next day, I will be starting to do more multiple choice questions based on this chapter waves. Okay, so thank you.